So check out the question. Calculate the current I, assuming barrier potential is 0.7 volt for the diode. Okay, asking that current I here. So this is the circuit of supply 2 volt is there. So this is 0.5 K. Diode with a barrier potential of 0.7 volt applied across 1 K. So now I need to calculate this current. For that, first I need to know whether the diode is on or off here. So now I can able to apply OC test now. Open circuit test now I can call. Means I assume that according to the OC test, diode should be assumed to be off. Now I can able to go to test this diode to be as a off condition now. So assuming that the diode is an open body, then what happen? You see this. This is the diode whose anode, cathode, consider the open circuit. Remaining thing as it is I taken now. 1K. This is 0.5 K here. Okay, this is a supply of 2 volt. Right. So because of the diode considers as open, this 1K and 0.5 K look like a series across this 2 volt supply. Then it look like a voltage divider. So based on that, I can able to calculate this voltage across 1K now. So using voltage divider principle, I calculate the voltage across 1 kilo ohm. That is supply voltage 2 volt into constant resistance 1K divided by sum of this individual resistance 1 plus 0.5. Okay. So this becomes 2 by 1.5. That is approximately what means 1.33 volt you can call. It is approximately how much means 1.33 volt you can call. So that should be what means greater than. So voltage across 1K should be nothing but same as voltage across the diode there. That should be what means greater than the barrier potential of the diode. That is 0.7 volt. So voltage across 1K nothing but look like the voltage across this open circuit diode you say. That is 1.33 volt. That should be greater than 0.7 volt you can call. So indicating that the corresponding anode to cathode potential of the diode should be greater than its cut-in voltage. So diode should be on, right? Therefore, diode is on. So once the diode is on, it look like act as a closed switch with the cut-in voltage maximum is 0.7 volt. Then whatever that equivalent model of the diode may come means like this you see. So this is the equivalent model of the diode you may get. So diode cut-in voltage is nothing but 0.7 volt you can call. So this is that. So anode, cathode, this is 0.7 volt. Diode you confirmed as a on switch, right? So this is 1K there as it is I taken. This is 0.5 K I can call, and the supply given is 2 volt. Right. So here he asking that current I. So you observe now, originally whenever the diode is open here, you said that the voltage is 1.33. But once you can able to keep that diode to be on, what is the maximum voltage across this parallel circuit means just only 0.7 volt only, not 1.33 volt you can call. Now the maximum voltage across that parallel circuit is just what means a common voltage you can call. That is what sir means only 0.7 volt you can call. Then whatever the corresponding current here means, see so now I equal to here 2 minus, so what is the drop here means 0.7 you can call, right? So here the voltage is nothing but 2 minus 0.7 you can call, right? So here this is nothing but a ground potential, that is 0 by 0.5 K. So this corresponding circuit having a maximum drop is 0.7 volt. So from 2 volt you have to subtract 0.7 volt, and then concerned current in the branch 0.5 kilo is nothing but 2 minus 0.7 by 0.5 K you can call, that is 1.3 by 0.5 milliampere. That becomes 2.6 milliampere you can call. So keeping the diode to be on, the voltage drop across the diode is 0.7 volt you can call. So because of 1K is parallel to this corresponding that, then maximum voltage maximum voltage drop across this corresponding 1K is just 0.7 volt only using parallel circuit principle. Then what is the voltage appeared across 0.5 K is nothing but 2 minus 0.7, that become 1.3 volt you can call, and the concerned current is I equal to 1.3 by 0.5 kilo comes to the numerator as a milliampere. So that become as how much means 2.6 milliampere. Okay. So check out the next question. Find the state of diodes D1 and D2 and calculate the current I in the circuit you can call. So these are the two diodes is given. Each diode have the same cut-in voltage of 0.7 volt you can call. And asking that which diode is on, right? Which diode is off condition. And asking that what is the current in the diode D1 you can call. So first I can able to go for OC test now. Now I can able to go for OC test. Open circuit test now. So assume that both the diodes to be off, I can call D1 and D2 are off. Assume D1 and D2 to be off. So diodes are D1 and D2 to be off condition, I assume. Now let us see this one now, the circuit I redraw. This one 1K. So this is the diode D1. So consider the off switch. This is the anode condition of D1. This is the cathode of D1, anode cathode. For D2, this is again 1K. So whose anode or cathode I can call? So this is A2 I call K2. Right. This is a supply of minus 5 volt there. This is a supply of plus 5 volt again. So now both the diodes have the same cut-in voltage. Now already I told that if the number of diodes are connected there, how do you know which diode conduct earlier? Means what is the diode which has more VAK, more anode to cathode potential that can conduct first. Now I can able to estimate what is that anode to cathode potential for both D1 and D2. This is for D1 I can call. This is for D2. Now I can able to examine what is the anode to cathode potential for D1 and D2 now, right? Now I can able to examine anode to cathode potential for D1 and D2 now. Okay. See this one now. For D1 I go. For a diode D1, anode potential you see now, because it is open, no IR drop here, so that IR drop becomes 0, so that anode potential is 5 volt and cathode potential is 0. For a diode D1, anode potential is 5 volt because 1K no drop, so anode potential is 5 volt, cathode potential 0, so that for a diode D1, anode to cathode potential is 5 volt. VAK1 means VA1 minus VK1, VA1 is 5 volt, VK1 is 0, that become 5 volt. Okay. Now for D2 now I can able to go that. So anode potential VA2 equal to 5 volt and cathode potential is minus 5 volt here. So because you have already open conditions, so the IR drop is 0. So 1 can look like a short there. So anode potential of D2 is about 5 volt. Cathode potential is minus 5 volt you can call. So VAK2 now I can able to go. So that is VA2 minus VK2 we can call. So VA2 is nothing but 5. VK2 is nothing but minus 5 you can call. That become 10 volt. So now I can able to compare the anode to cathode potential of both the D1 and the D2. On comparison, you say that anode to cathode potential of D2 should be more as compared to D1, so that D2 conduct earlier than D1 you can call, right? As VAK2 greater than VAK1. So among D1 and D2, D1 conduct first. After that, you can examine D2 for either on or off. D1 conduct first, right? D1 going to be, sorry, D2 going to be conduct first now. D2 going to be conduct now first as compared to D1. So as compared to D1, D2 going to be conduct first, right? Right? VAK2 greater than VAK1, D2 going to be conduct first, then compared to D1 you can call. Now I can able to rewrite that D2 as a closed switch, and D1 now I can able to examine whether it is on or off. Now I redraw the equivalent model of this. What happened now I can able to examine. See this one now. This is 1K. So keep that D1 as it is. I need to test again this anode, right? Cathode of this. This is for a D1 user. So D2 to be conducting you already know. So why it is look like be on, having a cut-in voltage or barrier potential is 0.7 volt, that I consider for a D2, that is 0.7 volt existing from anode to cathode, you say. This is minus 5 volt you can call, right? So this is a supply of plus 5 volt. In the first condition, you say that D2 on, D1 off, you say. Now I need to know the D1 is also on or off. For that, what will I do means I can calculate that anode potential of D1. I can calculate the anode potential of D1, right? By calculating this IR drop, concerned 1K drop I can calculate. For that, I assume that in this mesh, the current that flowing is some Ix. So in this mesh, what are the current that is flowing is nothing but I assume as some Ix here. By that, I can calculate the anode potential there. See, for now, what that value comes. So now I can able to go for the corresponding value of, so Ix value now I can able to calculate now. See, for now, Ix equal to, so this is a closed mesh. Here the supply is 5. Here it is minus 5 you can call. Here the drop is 0.7 you can call. So 5 minus 0.7 minus of minus 5 by these two resistors are in series, you can call 1K plus 1K, you can say 1 plus 1K ampere. So I can calculate the current Ix there in this closed mesh. So here supply is 5. Here the drop is 0.7, that to be subtracted. Here this is minus 5 you can call. So that becomes 10 minus 0.7, that is 9.3 by 2K. That is 4.65 milliampere. Right? So as both 1Ks are in series, the current Ix should be same in both resistors. So each is 1K, both are series. So the current should be same in both resistors you can call. Then based on that, I can calculate anode potential of for D1. VA1 I calculate. VA1 equal to 5 minus this concerned IR drop you need to subtract, that is Ix into 1K. So that is 5 minus 4.65 into 10 power minus 3 into 10 cube volt. So 10 cube 10 power minus 3 cancelled out. You may get 5 minus 4.65 volt. That become 0.35 volt. So which must be, so then what you can call means for a D1, okay, concerned anode to cathode potential you can calculate now. Anode potential is 0.35, cathode potential is 0, that become is 0.35 volt. So that is less than its cut-in voltage of 0.7 volt. So for a D1, the corresponding anode to cathode potential you may get 0.35 volt, which must be less than its cut-in voltage 0.7 volt. So based on that, D1 should be off. So here D1 should be off. So finally you can clarify that D2 is on state and D1 is in off state. So D2 is in on state and D1 is in off state you can call. And he asked that in the question, what is the current in the diode D1? As the diode D1 is open, the current in the diode D1 should be 0, right? As D1 off. So what are the current he asking through the diode D1? That should be 0 ampere you can call. That should be what means 0 ampere. So in the question he asking that what is the current in the diode D1 you can call. So that current in the diode D1 should be 0 you say. So this is the current in the diode D1, that should be 0. So next question you check out. Assume diode as ideal. Sketch V0 versus VA characteristic of a diode. So you consider that a diode should be ideal. Asking that what is the V0 versus VA characteristic graph. That is a transfer characteristic of a diode. So now you can able to check out. So for VA greater than 0 condition, for VA less than 0 condition, you test the output and then draw the transfer characteristic graph. See so now for VI less than 0 volt I can call. That is nothing but VI look like a negative there. So if I consider that VA negative, diode should be on condition, right? Cathode at negative potential, anode at positive potential, then diode look like what means on. Right? Diode it is on means it look like a closed switch, right? This is the equivalent model of it. This is R. Diode is ideal means no cut-in voltage there. So this is V0 you can call. This is VA you saying. This is negative, this is positive. Negative for VA less than 0 condition. So because it is a short circuited one, so that concerned output voltage V0 equal to 0 volt you can call. Concerned output is what sir means, so 0 volt. Now I can able to go for the next condition now. Now I can able to check out the next condition. For VA greater than 0 now. For VA greater than 0 now I can able to take out. For VA greater than 0 volt now I can consider that is VA should be positive condition. For VA greater than 0 volt if I apply, this is plus, this is minus, then diode is under reverse bias you can call. Diode should be open off. Diode is off state you say, open state. So once the diode is open, what are the equivalent model of the circuit means like this. This is R. So this will be the diode open. So this is the place of V0. This is the place of VA you can call. Okay. So because of the diode is open, it is an open mesh. IR drop is a 0 there. No drop across resistor look like as a short. Based on that, V0 should be equal to Vi. V0 must be equal to what means Vi. So for Va less than 0, V0 is 0. For Va greater than 0, V0 equal to Vi. So based on that, now I can able to sketch its transfer characteristic graph. See this one? So this is minus Vi, 0, plus Vi I can call, and concerned V0 I say. So now I can able to sketch the corresponding transfer characteristic graph he asked one. See this one now. For Va less than 0, V0 should be 0 you can call. This is the case. For Va less than 0, V0 should be 0. And for Va greater than 0, what you can call means V0 equal to Vi. This is the case. So this will be the transfer characteristic for that diode circuit. Okay. So this one now. Assume diodes D1 and D2 are ideal. He asking that sketch V0 versus Va characteristic graph. That is he asking transfer characteristic graph. Okay. So this is the circuit is given. Load resistance is considered as infinite there. That is open body. So D2 with the supply there at anode is about 5 volt is there. This is a D1 with the input of anode potential is Vi you can call, and it is about 10 volt supply. Let us see check that one now. For Va greater than 10 volt and Va less than 10 volt. By that you can identify which diode is on and off. Okay. So case 1 I can take out. For Vi greater than 10 volt. If I apply Va greater than 10 volt, the anode potential of D1 greater than its cathode potential, so that D1 look like be on. So D1 look like be on you can call. So D1 should be closed. Once it is a closed switch, you observe now this corresponding D2 whose cathode is at 10 volt, anode is at what means 5 volt you can call. For D2, cathode potential is greater than anode potential such that D2 should be off. Confirm now? For D2 you say cathode potential is at 10, anode potential is at 5, so that D2 look like be off state you can call. So finally you say that D1 on, D2 to be off. If I draw the equivalent model for this, that model to be like this. R, this is a 10 volt, this is Vi. Okay, so this is a D2 already off, so open. This is a 5 volt, open battery no use you can call. Already load is open, then this is the V0. So all are parallel together. What are the voltage across this branch should be same as Vi you can call. Based on that, V0 should be equal to Vi. This is the first case you can call. Now check out the second case. For VA less than 10 volt now. Second case now I go for VA less than 10 volt. If I apply VA less than 10 volt, anode potential of D1 less than its cathode potential such that D1 should be off. In this case, D1 should be off state. Okay. Once D1 is off, what happened here? This is the 10 volt that is given to the cathode of D2 whose anode is at 5 volt. So for D2 again, cathode potential is more positive than anode potential. D2 still to be off. And so now D2 at cathode at 10 volt, anode at 5 volt, D2 still to be off. And D2 should be off. So both D1 and D2 to be off. For VA less than 10 volt you can call. Then the concerned equivalent model may come like this. It is already open. So this VA, what you can call means no use there. Then what is the equivalent model means? Like this you see. This is R. This is of 10 volt. Okay. So D2 already off I told. Open battery no use. Load resistance is infinite means that is open, you know. This is V0. So this circuit look like a open mesh. In open mesh IR drop 0 such that V0 equal to how much means 10 volt you can call. V0 equal to what means 10 volt. So confirm now for VA greater than 10 volt, V0 equal to VI. For VA less than 10 volt, V0 equal to 10 volt you can call. Now you can able to draw its transfer characteristic graph. That is nothing but V0 versus VA graph for this. So V0 versus VA characteristic graph for that one I can able to draw. So this is that one now. So this is VI. This is V0 I can call. Now I can able to sketch out that. So for VA less than 10 volt, for VA less than 10 volt, V0 equal to 10 volt you can call. So this is that one now. This is negative VA. So like this, it is a 10 volt. Okay. So whenever VA greater than 10 volt, V0 equal to VA user. Suppose this is a VA of 10 volt now I can call plus 10 volt. So up to that V0 equal to 10 volt only. Once VA crossing 10 volt, V0 should be equal to VI like this. So up to 10 volt, V0 equal to 10 volt. For VA greater than 10 volt, V0 equal to VA you can call. So that should be the transfer characteristic graph for that.